Thank you, Mike, and thanks to everyone for still being here on Friday. At least all of you who are here. So, I'm going to talk about symmetric product codes. I guess I should note based on not really because of the theme of the workshop, but just by chance, this actually does make sense from practice to theory, because really the motivation to look at these codes came from the fact that people were using things in practice that really worked quite well. And then we decided to start playing with them and realize that there's some interesting things about these as well. So the beginning is going to be, I think, straightforward for many people, but at least we'll get our notation straight and talk about what we're doing. So we're going to assume that we have a linear NKD code. This, of course, means block length n, dimension k, minimum distance d, over some finite field f. We have a generator matrix and a parity check matrix of the correct dimensions. So the way I'm defining a product code is I'm defining an encoder where I take some information matrix, which is k by k of my field, and I'm going to do the standard encoding, which is UG, which would encode all of the rows. And then when I hit it with G transpose on the other side, I encode all the columns. So this is going to be the set of matrices where every row and column of the matrix is a code word of this code C. It is well known this is an n squared, k squared, d squared code. It's nice. Fits the description product code quite well. What we want to think about is what happens when we look at first symmetric subcodes. So what do I mean? I'm saying, so my code words here are these matrices. So I'm going to call them X. So they're n by n matrices. And I'm going to ask for the matrix to be symmetric so that its transpose is equal to itself. Okay. And so let U be the symmetric subcode. And in this case, what we can see is that if we're in characteristic not equal to 2, actually this constraint doesn't matter if you're going to do the proof more in a longer way. But it's easy to see that if you can take 1/2 times X transpose plus X, you will always get a symmetric matrix. And it turns out your code is given by this. Take all your code words, take the average of the code word and its transpose, and you'll get this. Now this matrix is going to still be n by n, but since it's symmetric, we might want to puncture the repeated symbols. So what we're going to do is puncture the lower triangle. And now if you count the number of entries in the upper triangle, including the diagonal of a matrix, you find there are n plus 1 times n on 2. And so we have an n plus 1 times n on 2. If you do another calculation, you find that whenever you encoded a symmetric information block, you got a symmetric code word. You can find the dimension then is k plus 1 times k on 2. And if you then look at your minimum distance code word and see how it projects down into this puncturing operation, you'll find that it's the minimum distance code words, which are well known here, become d plus 1 times d on 2. All right. So in some sense, what we've done is we've gotten a code of roughly half the length, half the dimension, and half the minimum distance. Whether this is good or not is not clear. Let's look at this in pictures. So we have our product code. Rows and every row and column is a code word of this matrix. And now what I'm going to do is the symmetric subcode, I'm just saying I'm going to just reverse these indices. So I put the same block in the lower part, and then I puncture it. All right. So what are the benefits? For moderate k and n, so the length and dimension is reduced by about a factor of 2. This can actually just by itself be beneficial in practice. So it's a code with very similar properties, but half the length and half the dimension, so roughly the same rate. And maybe this reduces your delay by 2. Of course, there's probably some penalty, but to first order, there's not much penalty. All right. Also, if you wanted to use the same component code, you're doing it using the same component code. The problem is the minimum distance also drops by 2. And so this is, of course, undesirable. Now let's think about what we might do to fix this. Let's instead take the anti-symmetric subcode of P. So I'm going to ask that when I transpose my matrix, I get minus X. If my field has characteristic not 2, that's sufficient to describe it. In characteristics 2, which is where we usually work, of course, minus X is equal to X. So this is becomes a trivial statement. So all we want to do then is zero out the diagonal. So the key element of this description is that it zeroes out the diagonal. And so now we can think of this. And fortunately, this description without the 2 there still works. If you take any code word and the difference with its transpose, that's going to have a 0 diagonal, even in characteristic 2. So you can basically think of encoding any 2 code words and taking their difference. Or taking any code word, its transpose, and taking their difference. So this construction, which is called a half product code, was suggested by Justison. And he suggested puncturing the lower triangle, this time including the zeros in the diagonal. And you're going to get an n choose 2, k choose 2, because now we're not taking the diagonal in our code, in either the information bits or the code bits. And it's going to have some distance. So when he suggested it, he stated that the distance is the same as before, d plus 1, or in this case, d choose 2. But that's not exactly right. All right, so in this case, again, I have our product code. Now I'm putting the whole thing in red to represent this is now the negative of this upper triangle. And then we're going to drop it and put zeros here. All right, so this is the main example. At the end, we're going to see that the idea behind this maybe occurs more generally. But we'll focus on this example. Now, to see how we came to think about these codes, let's start with a little background. So product codes were introduced a long time ago. Even the iterative decoding was introduced a long time ago. Even the density evolution analysis of their decoding was introduced a long time ago. Although it's actually hard to find. It's the proof of a lemma, which is in the appendix of Tanner's paper. You realize he's the first person to do density evolution for these codes, in '81. Well, just when they're Hamming component codes. All right, so what happens in the iterative decoder? We're going to show an example where we have 2 error-correcting codes with bounded distance decoding. So we're showing a binary array. The red marks indicate errors. And so we say, what happens when we decode the rows? Well, every row that has 1 or 2 errors can be corrected. Now we're going to make the assumption that we don't miscorrect, at least in this example. And so they'll be corrected. Now, when we do column decoding, every column which has 1 or 2 errors can be corrected. And now returning to row decoding, we get everything. This is the decoder that's used in practice. You can define a little more complicated decoder, which is easier to analyze and kind of provably works better, but nobody uses it. What happens to this decoder is it can get stuck in what's called a stopping set. These are the natural generalization of stopping sets in LDPC codes to this problem. They're well known. They get also related to cores and random graphs. So in this case, because I can only correct 2 errors, if I have any square submatrix which has a 3 by 3 set of errors, I'm going to be stuck. All right. So the application that I think brought these to the interest of people working in the theory of coding has been high-speed optical communication. So around 2010, Justison wrote a paper where he basically listed all variants of product codes that might be useful for this application. It's a nice paper in terms that but it doesn't say much about each one, but it says you can do this, 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 this. They should all work well. He's right. Of course, some of them work slightly better than others. Turns out in optical, they started with a 239, 255 Reed-Solomon code, so they like to match that redundancy in general. They always talk about changing it, but they don't really want to. And so the high-rate generalized product codes with BCH component codes appear as a very good solution in this case. In particular, there's this ITU document 975.1, which also suggests 10 different constructions of these types of codes, various generalized product codes. All of them work pretty well. Some of them work better than others. And so the decoding complexity, though, this is an important note, is much lower than comparable LDPC codes. I'm going to talk about why in the next slide. And for hard decision channels at high rates, the BER performance is comparable. So you can't even really beat them by much with LDPC codes in that regime. And so the key thing that I think makes these interesting in practice is the following. There's a very efficient decoder. And the decoder is based on syndrome-based iterative algebraic decoding. So what we do is we receive our product code word, and we calculate the syndromes of all the rows and columns, and we store those, and then we put the bits away. So for example, if I'm going to use a 1023-993 BCH code, instead of storing a length 1023 vector of bits, I'm going to store the 30 syndrome bits for my iterative decoder. So that's a factor of 30 gain at that point. So what I'm going to do is that I'm going to run algebraic decoding on each of the syndromes, and I'm going to keep track of where the errors were. There can't be too many because I can only correct 3 errors. And I'm going to update the column syndromes. And likewise, I'm going to run algebraic decoding on the columns using syndromes and update the row syndromes. So I'm not going to I'm going to put this other data aside and not even use it. My iterative decoder can use a much smaller memory that only stores the syndromes and where the locations of the errors are. In particular, the memory to store the syndromes is basically 2n minus k. So I'm assuming binary here. So it's 2n squared 1 minus r. Whereas if I had to store a log likelihood ratio for each bit in there, it would be order n squared. This calculation assumes that I'm going to store 3 bits for each LOR, which is, I think, a reasonable guess for LDPC. And in that case, my decoder, not really my decoder, the decoder people have been using in industry for a very long time, has a factor 50 less memory than a comparable LDPC decoder. So this is, in terms of power or running at high rates, this is an enormous difference. So, like I said, it's well known in the industry for many years. But, and then a few years back, we had a paper where we used spatial coupling to prove these kinds of codes with iterative hard decision decoding can even achieve capacity as the rate goes to 1. Now, of course, when the rate's going to 1, anything achieves capacity in some sense. What we mean by that is we're matching the redundancy, the first non-trivial term. So if you expand capacity about rate 1.
Just a quick question. For the LWC, are you assuming like edge storage? Like one?
No. No, I'm assuming non-edge storage. So I can, one per variable node. So I can put another factor of 3 in there, I suppose.
No, because you can do that.
So literally, I don't think there's any. I don't know of any trick for LDPC that reduces the memory to be comparable. So if there is one, I'd love to hear about it.
In the VCH, you're storing just 1 bit per.
Well, I'm just storing 1 bit for every syndrome. So I'm storing the syndrome. I'm not storing the information bits.
You have to receive values, right? You have to state, but you're just storing them as hard decisions, or?
Yeah. So
you get a factor of 3 right there, I guess. But yeah.
Yeah. So maybe it's not fair. So there's something hidden here. So let's think of it as memory accesses. For the LDPC decoder, I have to multiply this by the number of iterations. Here, I have to multiply this by the number of iterations. Of course, everybody has to store the received symbols. So we both pay as storage n squared, but I can put those in slow memory. I can keep them off chip or something like this. So, yeah.
Are you restricted to use this independent row and column decoding? You cannot make those decoding talk to each other, like GMD?
So I'm restricted to use syndromes. So GMD uses more than syndromes, right? It orders reliabilities. So if this is like the loss you get. If you're going to compress everything down to a syndrome, you kind of lose the soft information. So you could certainly do that for the decoder. I don't see how to use GMD with this low complexity decoder.
Okay, with syndromes, okay.
Right, so yeah, we'll talk about it some other time. What can I do more than this? I'm not exactly sure. All right, so what are we calling symmetric product codes? So we're saying we're taking the subclass of generalized product codes where we're going to use symmetry to reduce the block length and dimension while keeping the same component code. So that's the general concept. And so this example that I'm focusing on, which is the nicest example for say, is what's called half product codes by Justison. And when he introduced them, he actually credited them to Tanner. Turns out Tanner has a very similar construction, which we saw in Mary's talk. She had a nice picture of it. But it's not actually a product code in the sense that we want. It's just it's a nice graphical code.
For your application, what's your motivation for reducing the block length?
So let's see, what do I get? In terms of this, I can have a 1023. This is going to be a block length 1,000,000 code. So in optical right now, if I give them a block length 1,000,000 code, which performs the same as a block length 500,000 code, they take the 500,000 every time. Now, when I go from 10,000 to 5,000, maybe people aren't quite as interested. So this is a reasonable point.
They are still interested in Flash, for example.
But certainly, saving 500,000 of something seems more impressive than saving a few thousand. We'll see. I don't know. Now, so the thing I would say that motivated us to write this work up, we've been doing some of this, Krishna and I have been doing some of this work for a while, and we had a student who we said, give us a fair comparison. We kept pounding this guy to give us a fair comparison. And so he went away, and we essentially had not been doing fair comparisons, but we didn't realize it. And he said, well, I need to match between the product code, the block length, and the dimension. That seems like a fair comparison. So he goes out and he says, all right, well, we knew the block length would change by square root 2, and we kind of knew the dimension was square root 2. But we had never put these two together to say that means that the difference also changes by square root 2. And so that the half product code, to be fair, actually can correct square root 2 more errors. So if you build if you have a product code with 3 error correcting codes, you get a half product code in a fair comparison that corrects 4 or more errors. And so this actually changes a lot of the properties. In fact, it tells you that maybe the minimum distance isn't, because you're getting a better code, the minimum distances might even be in your favor as well. All right, so now I'm going to attempt one proof. Apologies in advance. I'm going to prove to you that the minimum distance of these codes jumps up by taking this symmetric or anti-symmetric subcode. And so to do that, we're going to have to do something that I'm sure many people know better than I, which is the idea of generalized Hamming weights. And so they have to do with the weights of subcodes of certain dimensions. We only need the very first one, so it's not too bad. What we need is the minimum over all pairs of code words that are not 0 and not equal to each other of the size of the union of their support. And so that means if you tried to take 2 code words and have them here and look at them in your combinations, it says how much room is that going to take? And we're going to see that's important. So it measures the minimum total support of 2 code words. Now there's a very simple bound on this. So you can say that has to be greater than 3 times the minimum distance on 2, and otherwise you get a contradiction. Because if you have 2 code words whose total support is too small, you can add them together and get below minimum distance. So the only thing you're seeing here is saying that if they're smaller than that, when you add them together, you get less than minimum distance. So it's a very simple idea. And so we have this. I think this is a well-known bound. I think it also appears in here. There's many more bounds that appear in here. I should tell you who that is. Heliseth, Clove, and Eutrius.
That was actually in Way's original paper. Way in 91 had all those bounds were these.
Okay. And even before that, in a paper that I didn't find. But I mean, right before that, right? Like
I cited Way yesterday.
What?
So Emmanuel mentioned generalized Hamming weights in his talk, and it was Way 91.
All right. So we're going to look at the anti-symmetric subcode, and we want to say this. For any 2 code words, we're interested in code words of this shape. And these are kind of like the canonical constructions of low-weight code words for product codes. You're going to take the outer product of 2 code words. Because essentially, if you take a code word on one side and a code on the other, and you take this outer product, that's going to be a code word in your product code. Because when you hit it with H on one side, you get 0, and it doesn't matter what that is. And so, but we want to show that it's not in the anti-symmetric subcode. So that means your minimum distance patterns with these blocks of 1s associated with minimum weight code words are not in your anti-symmetric subcode. And the reason is the diagonal is 0. So we're going to say because we're forcing the diagonal of our code words to be 0, we know that when we look at the ith entry, code word 1, and we multiply it by the ith entry in code word 2, it has to be 0 under this construction for all I. And then it tells me that these 2 code words I start with have to have disjoint support. Because if anywhere the support overlaps, they have a 1 in the same position, then I'll get a 1 on my diagonal. Okay? And now what I say is if I look at xij, so the ij entry in my matrix, I'm going to say that x1i times x2j is not equal to 0 for some point. Assume that is true. But now when I transpose it, it becomes x1j, x2i. I know that, so basically when I switch this one from I to j, these both have to be non-zero for this to be non-zero. And when I switch this one from I to j and this one from j to I, because the supports are disjoint, they both become 0. And so it says that if you choose the code word this way, it cannot be anti-symmetric or symmetric. So we'll leave it at that. So thus, any code word of this form is like this. So why does that matter? Well, let's think about code words of this form as essentially where you take one code word, say for your rows, and this x1 defines scalar multiples of it. So you're going to take one code word and just put scalar multiples in each row. And so it says there's no x and v where non-zero rows are scalar multiples of a single code word. So if they're not all scalar multiples of a single code word, there must be 2 code words, 2 different code words in these rows. And so now we say, because there's no scalar multiples, it must have at least 2 distinct non-zero codes. The minimum number of columns is therefore bounded by this second generalized Hamming weight, so it's going to be a little wider. And so likewise, just by trivial bounds, each column has to have d non-zero entries. So I get a bound, instead of d squared, I get d times d2. Right? So minimum distance of my anti-symmetric subcode is d2 times d, which I have this lower bound. All right? When I puncture, it's symmetric, and I've dropped out the 0, so I'm going to get half as many 1s. And so now I can divide again by 2. So puncturing to get my half product code, which I'm calling this script h. And if d is even, this comes to a simple form of 3d squared on 4. So basically, I'm getting a factor of 3/2 gain over my minimum distance. So it's not an amazing factor, but it's enough to make this code basically as good as the full code. And so now I've got a code that's half as long, that's basically as good as the original code. So that's the kind of practical motivation of this. Now, if you work this out in more generality, you get some, things like this. There's a matching upper bound in some cases, so you know it's tight. We could probably make it match in all cases with just a little more pain. So I'll repeat the basic idea. So zeros on the diagonal present the standard square pattern code words you get in product codes. Once those go away, you kind of have to look at the next weight, and that involves the second generalized Hamming weight, and so you get this bound. So let's do an example. So we say now if we have an 844 extended Hamming code, it turns out in this case my minimum distance is even and my bound is tight. And so what I see is that I get a half product code, which is a 28, 6, 12 binary linear code, because I'm going to have 3 times 4 squared on 4, which is 12. And if you look in the table that's now compiled by Marcus Grassel, I can't remember who, maybe it's originally Brouwer's code table. No binary linear code exists with larger minimum distance and these parameters. It's a fairly weak statement when you look at these tables, but it's a true statement. The upper bound does require, essentially, when you find the minimum for the generalized Hamming weight, you have to have points that achieve it. You have to find the code words that achieve it and calculate something. So to make it a tight bound. All right, so now we have some idea. So this in particular, I don't think this holds for any product code. There's no product code that when you take the product code, it actually has the best minimum distance for those parameters. Maybe it might be true for like a single parity check or something, but even then, I don't think it is. All right, so now we want to use iterative decoding, as we talked about. There are some analysis techniques. So basically, we're going to assume, because it makes our life easier, that the received symbols can be corrected sequentially without mistakes. This always works on the BEC. On the BSC, we have to assume there's a genie that keeps us from doing miscorrection. The way it works is it's based on an error graph. So what you do is you're going to take every code constraint and call that a vertex. This is actually Tanner's representation of these kinds of codes. And every edge is really a variable node, and it connects the 2 code constraints which it's in. And when you have the initial observations through your either erasure channel or error channel, everywhere you get it right or you observe it, you can remove that edge. There's no problem. And so now you have this thing. So what you have here is you started with essentially a complete graph or maybe a complete bipartite graph. So in the product code case, it's a complete bipartite graph. In the half product code, it's a complete graph. And you've removed all edges independently with probability 1 minus p. So you have an Erdős-Rényi random graph. And so it turns out, if you think of your decoder that peels any code constraint which has t or fewer edges, this will always reach some stopping state. You're peeling your graph down after a finite number of iterations, and some nice things happen. In particular, you can have asymptotic results that are in this regime, where the lengths of the codes are growing without bound, but they're correcting a fixed number of errors, say 3 error correcting codes. So of course the rate's going to 1. It's a little bit of a strange regime, but this is where you can actually prove something. And so we say is n's going to infinity with fixed error correction t, and I'm assuming that my error rate scales like lambda on n. And this is actually the same as the Erdős-Rényi sparse regime, so that's nice. The decoding threshold can be seen as comes from graph theory in solving the K-core problem. This was observed in 2007. And if you look at the thresholds you get, so if you assume you have 2 error correcting product codes, and actually I should note this, the problem is the same for the product and half product. So essentially they have the same threshold. So if you take the same component code, half product and product have the same threshold. Now first that sounds like I've done something. Wow, I have half a long code. But since n's going to infinity, that's kind of a vacuous statement, right? I have code that's half as long with n going to infinity. They're both going to infinity. But for t equal to 2, 3, and 4, I can find these thresholds. It says if you have 2 error correcting codes, you can basically handle an average number of errors of 3.35 in each code. If you have 3 error, you get 5.14. And yeah, now you can kind of extract some finite length information from this. If you think of this as a sequence of thresholds that depended on n, you know that this limit has to be equal to these lambda stars. And so if there's n is large enough, you can kind of guess. It's not provable a threshold from this.
For the BC, you still have, I mean, this still assumes they have some kind of genie or something. Right?
Yes. So this leads us to an open problem. So you can make this analysis rigorous if there's a genie preventing miscorrection. You can use a much more random graph and make it rigorous using density evolution if you have miscorrection. I do not know how to make this analysis rigorous with miscorrection. I think it's possible. But what you have to do is you kind of have to have a slight correlation between your errors and still have it work. So, because what happens is when you miscorrect, you always go to a code word. So the errors have some structure, and they just don't have very much structure. So, does that answer your question?
But in practice, do you see that? Or do you see that?
So in practice, if you want to get the right threshold, it's better almost to assume you have miscorrection and your graph is completely random. And so like this is the analysis we did for GLDPC and this kind of thing. That gives you a better estimate of the threshold.
This may be a strange question. How much more do you have? Just curious.
4.
4? Okay.
How much?
When did we start? 11:06.
5 minutes after.
Okay. So it's just...
2 minutes?
Yeah, you're fine.
I think it's fast, but we'll see. All right. So in fact, it's just plots and description of plots. So I wanted a fair comparison. So because of numerology, I can't get an exactly fair comparison. So I had to match the rate exactly and let the block lengths differ a little bit. So my product code is a 170, 154 shortened BCH code, which corrects 2 errors. Its minimum stopping distance is 9 in the iterative decoder. If I take the half product code, I can get a 3 error correcting code. And the block length's a little longer, but it has exactly the same rate. You'll see its minimum distance is larger because it's this anti-symmetry. And even its stopping distance is larger because I went to a larger code. Okay? We do iterative decoding, again, assuming the genie. Now we can guess these thresholds, and if we use the guesses, we see that we expect the half product code to perform better than the product code from a approximate analysis of density evolution. And when we do it, we actually see that. So we see the blue curves are for the product code, and the red curves are for the half product code. And you can also write down the error for. The error for is actually going to be lower for the half product code as well. But we'll never see it. It's 10 to the minus 14. Or we won't see it with my simulations. How's that? We need hardware. Okay? So that it's not, there is some gain here. All right? And so the other thing is now what happens when we go, so that was going from a 2 error correcting code to a 3 error correcting code.
So the total length was what again? Was like square, or what was the length here?
Yeah, so 28,900 here and 32,000. So these are not obscene lengths, I don't think. All right, so now we have a case where we don't get better, but we know why we don't get better. So the product code is now a 3 error correcting code, and it has rate 0.86. Here's its parameters. And the half product code is based on a 511. Did I say that right? Yeah. 4 error correcting BCH code. Here's the length. And what we see now is its stopping distance is slightly lower. But the bigger problem is if you use density evolution, when you go from a 3 error correcting to a 4 error correcting code, you actually don't get as much as you should. It's a lot like raising the degrees of your LDPC code. You say, I'm going to go from degree 3 to degree 4. Oh, that should be better. But under density evolution, it's not. And so you have exactly that loss. Now, as we've heard many times, we would expect if we spatially coupled these, which you can do, they're called braided block codes, that would go away. So this one, we actually see the product code performs better than the half product code. All right, so my conclusions. So half product codes, the length and dimension are basically reduced by half with the same component. The normalized minimum distance is basically improved by 3 halves. And for the same block length, you can increase t by square root 2. When you go from 2 to 3, this almost always improves performance. From 3 to 4, it's a little more of a wash or slight loss. Now, in terms of open problems, and this is in this ITA paper we have up, there's a natural generalization to this to m-dimensional. You pick an m-dimensional product code with the same code, you acquire the whole thing as an anti-symmetric tensor. That means when you look at it, you interchange any two indices, it negates the value. Almost everything goes through. You can show that the minimum distance again is going to jump up, but we couldn't figure out by exactly how much. It didn't have such a nice simple characterization. But we think it could be large. Let's say this. It could be as large as exponential in m. So with that, I'll stop.
Two questions about the last remark you made. It doesn't show up anymore as a generalized Hemingway 3 or 4.
So my guess might be that it's the product of D, D2, D3, D4. I couldn't prove that. I don't even think it's right. That was my first guess.
Okay, so it's a product of the higher weight.
Well, no, that's just random guess. So we played with it, and we did not get anything. So I guess you can show, at least you don't lose when you go to the third dimension. You've already gotten a little larger. But it's, I don't know. It's either more complicated or there's a trick we didn't see.
And one more question. You showed all the examples for BCH codes.
Yes.
All your codes were BCH. Can't you choose the component codes in such a way to try to optimize the stopping distance, or try to come up with a better choice for the component code that would boost your stopping distance?
So the only better choice in these regimes than Hamming codes would be or BCH codes would be preparata or Kodak codes. And so yeah,
You can compute the stopping distance, or did you compute it by search, or do you have a formula?
No, I can show you the patterns. So the stopping patterns are these little square patterns, maybe with a diagonal missing. They're kind of.
Just the.
So you showed example that you get the best linear codes, 28.
Wait. I wouldn't. So we have a code with a certain NK and a certain dmin, and there's no code with that NK and a larger dmin, linear. Yep.
Do you know of other examples that you can?
Yeah. So the same, that was the 844 Hamming. The same thing happens with the 743 Hamming. Same thing I think happens with the single parity check. I have a guess of maybe one more, but I don't know of any more for sure. So, yeah, it's probably not true. It's really because they're small and everything's just right. It's not going to be a general statement for sure.
So just following up on that, what about higher dimensions in 3 dimensions of the Hamming code if you take it?
No, in the paper I mentioned, I give a construction for the 3-dimensional one. It does not have that property. So it's minimum distance, like we could try and guess the formula from it, but its minimum distance does go up more than you'd expect. I don't know the formula. It does not match the best known code. So.
Thank you.